All right, hey, we are going to be talking about uniform circular motion this time around. So the biggest thing when we say uniform circular motion, what we mean there is that the speed is constant. Now you might notice that I just used the word speed instead of velocity, and that's because we can't say that delta v equals 0 because we know that velocity is actually a vector, and if we are moving in a circular motion, direction is always changing. And if direction is always changing, then of course there is a delta v, and there is an acceleration. So what we're going to look at in this example is trying to understand that A a little bit better and how to find it. So the first thing that we're going to need is a circle. We're going to use that as our circle. And then we're going to need some velocity vectors. Now, because the speed itself is not changing, all of these need to be exactly the same size. So we're going to kind of just copy and paste this one. There's our first one. We'll come and move it up here to the top. It's kind of hard to get there, but we'll get it as close as we can. We'll move this one. It'll be our first one. We'll get it right as close as we can again. And so once again, all of these are representing our velocity vectors. So they're all going in different directions, but they're going to be the same exact size. Now, when we've talked about in earlier classes, is in order to find A is in the direction of delta v. So that's what we need to look at, is some of our delta v's. So this guy over here is what we started with. So we're going to use him to go ahead and get started. What we're going to do is we are going to do v1 minus v naught. So we're going to use this guy to go. Actually, might just erase them. We'll get started again. v1 is this guy at the top, so we need a perfectly, horizontal one. And then v naught, we're going to do a negative v naught, so we need one going in the down direction. And we can do our delta v connecting them. So we just did one here, and that's a really big vector, and it's going in the slightly kind of 45-degree angle there. But I want to see what happens as we change the vectors that we choose, because we know that in our level math, we always want to know what happens when delta t goes to 0. So we don't know how much time there was between v naught and v1, but we know that some time passed in order to be going in this direction to now be going in this direction. But in reality, there were some other ones in between. There was probably this guy. And we can just call this some v after time. So let's see what the delta v for that would be. So we need to start with him again. We'll try to get about the same angle we had. So this would be our v delta t. We're still going to need our v naught. And we can go ahead and do our delta v. So you can see simply by changing the initial position of our final velocity vector, so changing the position of our final velocity vector, the direction of our delta V changed a lot. This one looked to be very steep. This one's kind of flattening out a little bit. So we can go ahead and do that again. And let's make our delta T even smaller this time. So we know that we originally started vertical. So our delta T, if it's not very small, it's only going to give us a slight angle here. Then kind of zoom in a little bit on this guy so he's not taking up so much room. So we're going to get really close to him with this next V. So we know this one was originally vertical. We're going to go ahead and put it in there. And if we do that delta V again, well now, this delta V is almost flat. So the relationship that we're seeing here is that as delta T goes to 0, delta V is becoming perpendicular. We're getting that perpendicular. And this we do want to talk about from where our V naught was. That is the one that we are recognizing here. So it's almost a perpendicular relationship with our V naught. That's going to be really, really important. If we come up here and we look at that, the perpendicular position to V naught in that correct direction is actually pointing towards the center of the circle. So we could see, we actually visually did it here, that we kept getting our delta T smaller and smaller and smaller until we did this last example. And when we did this last example, we had delta T as small as we could. So we had our original vector and then a vector that was just ever so slightly different as it made its way around the bend of the curve. And we can see that our delta V is almost perfectly perpendicular. There's another way to think about this. As you saw me draw these, you saw that I was using the same exact vector and then just changing the direction for each of the sides of my triangle. That means that each of these are an isosceles triangle. When we are in an isosceles triangle, you hopefully remember from your geometry classes that the base angles are congruent. So when once again, when you're here, you know that your base angles are congruent. We also know that all angles in a triangle sum to 180 degrees. Well, if we keep thinking about this, once again, we want to do it as delta T goes to 0. But as delta T goes to 0, that means our change in theta is also going to 0 because we're trying, if there's no time passed, we haven't moved at all. Now the theta would be the theta between our two vectors. So it'd be the theta at the top of our triangles here. That's what we're talking about when we're talking about this delta theta. That means that these two bottom ones that are the same would be having to sum to 180. In order to do that, because they are congruent, we saw that, you would say 2, let's just call them 5 for now, would have to equal 180. So 5 would have to equal 90 degrees, which once again is that perpendicular relationship. So the key takeaway here, hopefully, I always try to show you guys why things work, but the key takeaway is that when in uniform circular motion, A is always perpendicular to V. And that is what we kind of tried to show in these two different examples, is that your A is going to be perpendicular to your velocity. Now, before we get too far about actually calculating A, I want to remind you guys that vectors can always be broken down. That says down. Let's try that again. So vectors are always going to be able to be broken down to those perpendicular components. So often we do x and y. But when we're dealing with circular motion, we're going to do centripetal and tangential. So centripetal is towards the center of the circle, and tangential is along the path of the circle. So if we come up here and even just look, we can see because our velocity vector here, our acceleration vector here is towards the inside the circle, that it is a centripetal one, versus all of our velocities here are perpendicular to the circle themselves, so they are all in the tangential direction. So whenever we're talking about uniform circular motion, that is what we're talking about. We're going to break things down to centripetal and tangential, so towards the center of the circle or along the path of the circle. Well, once again, in uniform circular motion, the tangential component of acceleration is 0. That is why our speed is not changing. But we know that there has to be some sort of centripetal acceleration in order to make the direction change, and that's what we looked at above. So the next thing we need to do is figure out how can we calculate centripetal acceleration. And we're going to be looking once again at uniform circular motion in order to create this. So we need to go back to our circle here. Okay, so whenever we're center of our circle, we know from the center out, these are our R's. So I'm going to call this one R and this one R. After some time, this would then be theta, and between them would be our delta R. So just created a nice little triangle there for us. But also, we know that if we are at R here, there's some velocity here. And then there would be some velocity at this new one. We can bring them over here and create that same type of triangle again. Okay, and our theta would be here as well. One of the things that hopefully you're noticing is that I just created two isosceles triangles. Because this is a circle, the radius is obviously the same. We're talking about uniform circular motion, so our velocities, oops, you know what, let's change colors. Our velocities are the same. So this is a really cool idea that we just created two isosceles triangles, and then also their theta is the same. This theta here and this theta is here are going to be the same because they traverse the same amount of distance. So because they are connected together, in order for R to get here, V had to go through the same arc, which we know central angles and their arcs are the same, so they traverse the same amount of directional change here. What that pretty much just means is we just created similar triangles. And throwback, that would be your side angle side, side angle side kind of relationship there. So they're the same type of triangle and they have the same exact angle. And so because they have the same angle, same type of triangle, we can go ahead and make some relationships here. We can put their side lengths and proportions. What that really means is that we can say delta V over delta R, so those were definitely two of our side lengths, of delta R and delta V here, can be equal to V over R. And do make sure, once again, when you're doing similar triangles, that the same triangle's on the top that is on the bottom. So now we have a statement that we can use. And once again, we are able to make this because we just created these two similar triangles from the situation of uniform circular motion. Now that we have them, we want to manipulate them somehow. So people have worked with this for a while and they figured out, you know what? What happens if we multiply each side by delta R over delta T? Well, on this side, my delta R's cancel, leaving me with delta V over delta T. Here I just have V over R times delta R over delta T. But once again, we're going to go back to that idea that delta T needs to be going to 0, because once again, we're always talking about that instantaneous, at that moment while we look at it. Well, as delta T goes to 0, delta V over delta T does become your acceleration. And then delta R over delta T actually becomes your velocity. Well, so that becomes velocity times velocity, which is velocity squared. The only type of acceleration we have here is centripetal. So this is actually our equation for centripetal acceleration. And once again, this only worked for uniform circular motion because this whole setup came from these isosceles triangles, and we would only have isosceles triangles if the actual quantity of the velocity wasn't changing. And so because that quantity wasn't changing, we could create these isosceles triangles, we could create this relationship, and now we have a new formula. So this is a formula that we'll be using often in class when we start problem solving with uniform circular motion.